Summary. Further considerations of reading the sky, including blue day screeting. When we're flying along, we might consider that we can see our clouds and we don't pay enough attention to hitting the center core. So we simply maintain track with the wings level. And we are going to assume that that's what we will achieve. In reality, though, remember, there's always an outflow if we don't hit the middle of each core. So despite the fact that we keep the wings level, and certainly if we look at the string, we will see the string shove over, and then it will come back to the straight position, the balanced flight. But what's actually happened is the glider has been shoved sideways. So we don't really get as much of a benefit routing as we thought we might. So we need to pay more attention to making sure that we hit each cell head on, so that we end up flying through the maximum amount of beneficial air and avoiding the bad air. Of course, what happens to the vortex at the inversion then? We can see that as the cell hits the inversion, it continues to roll outwards like that. And we see this from the vortex cloud that's formed, the ring cloud, and we can see the ring of cloud cascading outwards before it completely dissipates. Why spread out appears so quickly? Because each of these cells go up and roll outwards, and lo and behold, we end up very, very quickly with the sky covered in a thin layer of cloud, which cools the day off somewhat. So here we are under a sky of spread out, and you'll see the slightly darker cells appearing and disappearing. Of course, spread out would lend itself to this kind of pattern, the heptagon pattern, in the same way that we observe the changing generation of cumulus. We can also monitor the rates of change in the size of the darkest areas under spread out, but only in the afternoon. Pressing on under morning spread out is likely to be a field landing. Of course, reading spread out is more difficult than you think. There's more than 50 shades of grey for sure. So let's just introduce another square B. And square B throughout this is exactly the same square B. In other words, the greyness of it is exactly the same wherever it travels. And we can see the greyness of it appears to change depending what the background grey is. So it is in fact very difficult to observe this development of cumulus under a spread out day. Consider trying to remember a mobile number for 30 seconds. Then identify how, given a few changes in the number, whether you could readily identify the changes. It's unlikely. However, if it is just 3 or 4 numbers and they change, you probably could identify the changes. If we look at the sky at any one moment then, we could identify where we think is a good place to go and perhaps an area where it's not looking so favourable. So here we give relative values to the anticipated thermal strengths of the clouds below, assuming that the best climb you have had so far was 6 knots. bearing in mind that there can be a variation of thermal strengths in any air mass. So on the left, we're going to say that its thermal strength is 1. If you wish, it's an embryonic thermal, or it might be a dead thermal. We don't know, because right now is the first chance we've identified it and given it an assessment of value. The next cloud looks relatively average at 3 knots. The next cloud is looking strong at 6. The next at 4, which is a broader cloud. And finally, the one at the right looks a nice, good, big, strong cloud. And so we're going to say that its potential is a 4-knot climb. So in any snapshot, we can make a suggestion of how strong the air is ahead of us. But remember, it's a game of chess. As we set off, we find 2 minutes later, as we're approaching the clouds have changed. And this is the picture we have in front of us. So now we may well think, well, where are we going to go now? We would again give an assessment of how strong each individual cloud is and perhaps make a decision. So we look at this one on the left and we think, well, that's 3 knots. And sure, the next one's looking 4 knots. The third cloud is at 4 knots. The fifth at 6 knots. And finally, one at the end. Wow, that looks really fantastic. That's like 7 knots. The strongest thermal of the day that we have seen. However, this thought has got to be in consideration of what we saw before. So the cloud on the left has gone from a 1 to a 3. So it's clearly developing. The second one has developed from a 3 to a 4-knot thermal. So that is still developing. We may well consider that to be 5 knots by the time we get there. The next one is the strong cells, though. 6 knots is now 4. That means it's dying. The next one, 4 knots to 6. Well, yes, but 2 minutes later, it's going to look like the one to the left of it. So it is dying. And finally, the bolt from the blue 7 knots, bolt from the blue 7 knots on the right, well, that's clearly about to die completely as well. So in reality, the clouds we want to be going to are the 2 on the left to stand a reasonable chance of actually getting a climb. Here we see a picture of real clouds. We just call it A, B, and C. We could call it the baby or dead cloud on the left, daddy in the middle, and mummy on the right. It really doesn't matter how you identify strengths and weaknesses, entirely up to you. But you need to know what they were and what they're changing into. So if we look a minute later, we can see that the embryonic one was exactly that, and it's strengthened into a teenager. The 2 stronger cells on the right, though, that were previously daddy and mummy, well, certainly mummy is not looking very good, and daddy, well, it's not as strong as it was, though we have to anticipate that maybe it is decaying. If we look 1 minute later, we can see the baby has become daddy, daddy has become dying, and mummy is dead. Consider doing some recordings of a time-lapse video of the sky, learning how the sky rotates. Video any active sky and review it by time-lapse. You can set it up on the bedroom window for a few hours, or until the battery goes flat. Save the clear ones that you find useful to remind you of how the sky changes, and abandon the poor ones. Of course, to do this costs almost nothing. And of course, you can record the sky at any time You don't have to be just at the gliding club to do it. We do get thermal stacking, and consider below the bus traffic jam. So the buses are going along quite happily right to left, but then they're slowing down on the left. So the distance between each individual bus reduces. They're separated by time, not distance. So here we have thermal stacking. As the thermals approach cloud base, then you find that they will slow a little, or they may slow a little, and therefore you'll end up a number of cells relatively close together, which is fortuitous for us if we're cruising through them. So the benefit if clouds show the development of weaker thermal hits cruising into wind at height is considerably greater than the thermal hits lower down. So here our lower man has got quite a long way before he hits the thermal, whereas the guy at the top can cruise quite happily. Although it's weaker lift, he's losing no height, and of course gets much further upwind, as it were, than the guy who's lower down, and he maintains the height. So thermal stacking can aid to an efficient cruise, and bear in mind the thermals are slightly wider at height. If we look at a single streaming source, then street, the bubbles are blowing off routinely and climbing. As they approach the inversion, they slow. The vortices will continue to rotate. Blue days are not the strongest, and bubbles spread and weaken towards at the inversion. Buoyancy here will depend on humidity. Looking down from the top then, here we've got 3 single streaming sources. Bear in mind that as they reach the inversion and slow, the vortex will distort before it breaks. So it'll widen across the wind, but not along the wind. So now we can consider our blue day streeting. The bubbles will come off, but as they approach the inversion, remember, normally the wind will increase and veer with height, and so here depicted just what happens to the cells as they climb up. No point driving into wind from a thermal source. From leaving a thermal, chances are you won't hit the thermal. You need to go significantly crosswind until you hit the next streaming source, and then work up that line, find a cell within it, climb up, and then move on. The width on a blue day is purely controlled by the thermal sources and not the height of the inversion. Blue thermal disparity. Assuming that the glider falls at 1 knot, the drag of the vortex in this situation is about 2 knots. And sink is proportional to lift. So the drag of the vortex is proportional to its buoyancy, i.e. speed. So this rate of ascent here in an unstable layer is relative to the real world. So the thermal is going up at 5 knots, and the glider in the centre core will climb at 4 knots. As it transits through the sink of the cell is around 3 knots, so the glider will experience 4 knots down. Blue windy day streeting. So here we are flying block speed over 60 knots. If we're flying in this band here, the lowest level, obviously each time we hit a thermal we'll have a reasonable rate of climb. As we climb up, the thermal strength will weaken, and so our average rate of climb will reduce. So our performance and speed around a task reduce quite rapidly. So where we have our little races, then basically the guy who dares go lowest will be the fastest. Only here we have a line showing roughly the average speed round a task. It diminishes as we try to maintain a higher height. When we're in very hazy weather, diagonal visibility ground limit through thicker haze. As you get lower, you actually see less ground distance ahead. Diagonal visibility in cloud limit through thicker haze. As you get lower, you see less cloud distance ahead. So whenever it's hazy like this, or very hazy, as it used to be in the olden days with stubble fires, then it was worthwhile always climbing higher in the weaker thermals so you could see the next cloud ahead, because as soon as you descended 500 feet into the haze, you couldn't see it. Blue day losses through turbulence. Note that on blue days, or any sky where the majority of the thermals are generated by heat, there will be greater losses due to turbulence and an inefficient glide. Bug factor needs to be increased to reflect the real-life performance that you might expect. And here we have a day of bubbles, not columns. Wind shear on the structure of cumulus. Here's a common diagram. Bearing in mind all that I have said, can you identify what is wrong? The answer is the bottom green lines. There's no diagonal updrafts. Rising air only goes one way, straight up. Wind shear on the structure of cumulus then. Here we have our wind shear, and that is wind shear above cloud base but before cloud tops, blowing the thermal over, blowing the cloud over, causing far more evaporation on the downwind side. And that will give you quite a broad band of quite significant sink. In this situation, it's unlikely to get any cloud suck, but there will be a vertical wind. Three types of cloud then. Here we have the classic cumulus reducing in width with height. Here we have our towering cumulus. And lastly, we have widening cumulus with height, i.e. the anvil thunderstorm clouds. The thing is, why does this happen? Ice crystals then, at -4 degrees centigrade, are light. They're less dense than any kind of water droplets. Ice crystals also don't evaporate as quickly as water droplets. We get reduced sink generation because there's no evaporation, and hence this shape above. Small cloud cycling. What does a cycling cumulus look like? Well, it'll like this. Consider the steam from a kettle. As fast as it is forming, it is evaporating away. It forms as classic sign of wave interfered cumulus. The cloud rarely drifts downwind, but quickly becomes destroyed if it does. Leaving upwind, you enter very smooth lift and no sink. To enter, though, you must ideally accelerate in the lift and pull up on the leading edge. Weak thermals. Note, with high humidity, at cloud base the cloud forms quickly but is slow to evaporate. Thermals are characteristically weak because there is little sinking cold air to reinforce the lift, and there are large areas of shadow. The misleading bubble day. Just because the cloud looks good and assumed to be a column day, it might not be, especially on hot days with a southerly wind. The problem might be anticipated if the humidity at height is known. Bubble day, big clouds with no cleared side walls and no rotation at the sides. Column day is big clouds with rotation and defined sides. Basic difference between bubble and column clouds then. Bubble cloud, a flat vertical development. Big clouds become ragged quickly. Column day, column, all big clouds show development. A dry bubble and moist column thermals. Here we have two bubbles rising up. The one on the left is purely temperature driven, so a thermal. The one on the right has got thermal buoyancy and humidity driving the buoyancy. When they become a co-temperature with the environmental air, so we've got a thermal from a dry solar farm into moist or co-moist moist air, buoyancy due to temperature, the structure will collapse and it's gone. If we have a thermal generated from a pig farm, it's moist into dry air, the buoyancy due to humidity will continue and the thermal may even accelerate upwards into the inversion. Here we have a series of pictures. The cloud base is 5,000 feet. The question is it a bubble or column day? Hopefully you've already identified which it is. But there's also a bad technique being demonstrated by the individual in the front. The time shots are taken at 10-second intervals, so we're playing this effectively at real time. And the question is, what cloud are you going to go to next? Okay, so you can see we didn't stop for any thermals on the way, and sometimes people say, well, it was a difficult day. Actually, they don't really understand what they're seeing. Here we have cumulus over the sea. Nice, even a street. Where is the hotspot? Here we have a far more complex structure in the sky. And this was observed by chasing after a couple of buzzards. In the first one, there's a little bit of a cumulus formed. I climbed to about 1,800 feet. The buzzards didn't go upwind, they went downwind. Feeling this might be a better idea than our plan of just going upwind, chased after them. Of course, what had happened is the initial cell had formed a cloud into the dry air at the upper inversion. That had cascaded into sink. Followed the red line down, and this made a small splash in the very humid lower level, which kicked back and generated another thermal. This time, climbing with the buzzards, we make 2,500 feet. Sure enough, the cloud disappeared, the buzzard disappeared. Time for us to follow them further downwind. A couple of kilometers later, of course, the cloud had evaporated. The sink slug had come down, splashed into the lower layer. Humid air kicked back, made another thermal, and we get a climb to 3,000 feet. We would never have known that if we hadn't chased after the buzzards. So it's not your traditional tuba sink. The splashback mechanism then, humid air and dry air at the inversion, and therefore climbing above the inversion. So here we have what happened. The sink from the evaporated cloud is just like a droplet forming into a cup of tea. So consider a drop of milk into a cup of tea. As it goes in, it makes a splash, and the tea around it gets splashed back. Of course, in this case, we're talking about humid air is kicked into dry air. As it rises, it suddenly gets a little bit of buoyancy. Draws up a little bit more, and lo and behold, the vortex that we know and love is generated. Once the vortex is travelling, because of the humidity in it, it will continue to do so upwards for some height, just like a smoke wing will. Humidity differences may continue the push, just like humid thermals climb above the inversion. And that's exactly what we experienced on that day. Summary: further considerations of reading the sky, including blue day streeting. What can you see in this simple picture? Dark spot under the cloud. That has to be good. The darker the area, the higher the humidity. The greater the humidity, the greater the buoyancy. The greater the buoyancy, the stronger the thermal. Over here on the right, we can see light base with bad striations, and that's dead air. And in terms of blocks of air, we're looking at a good block, but to the right is a big blue block. So the properties of those two air blocks is different, which is why clouds on the right are essentially dying. This particular cloud here is elongated. We have a reverse thermal just to the left there. We have lines of energy which we can use in more than one direction. Dark areas under clouds, light areas under clouds is bad. Dying cumulus, elongated thermals, a reverse column thermal, streeting, and cloud tops are leaning. That's leaning, that's leaning, that's leaning, that's leaning. So it gives an indication of what's happening near cloud tops.